Section: Introduction. In this section, we explore the remarkable flexibility of modern language models, LMs. Unlike traditional neural networks that are designed for specific tasks, LMs can be prompted with natural language to handle a variety of tasks. This ability, known as in-context learning, ICL, has transformed natural language processing by allowing quick task adjustments without the need for costly fine-tuning. However, the mechanisms behind ICL are not well understood. Some studies suggest that ICL may not be true learning but rather a way for the model to choose familiar tasks from its training data. We also note that the design of prompts is crucial, as the selection of examples and output labels can greatly influence performance. Yet, much of the existing research has focused on how LMs respond to inputs, leaving the internal workings of ICL largely unexamined. Our goal is to shed light on ICL by studying how different prompting methods change the internal representations in pre-trained language models. When we prompt a model for a classification task, we will analyze how well separated and geometrically structured the representations of different categories are within the model's embedding space. We will use a framework called manifold capacity, which connects task performance to the geometric properties of these representations. Our main contributions include a thorough analysis of how various prompting methods influence internal representations in language models, revealing different computational mechanisms even when performance appears similar. We will also provide new insights into the dynamics of in-context learning, such as the significance of label meanings, the combined effects of demonstrations on unrelated tasks, and the trade-offs in representation during task adaptation. We recognize that prompting allows a language model, which has been pre-trained to predict the next word, to adapt to various tasks without changing its parameters. This process, known as ICL, enables the model to learn new tasks by drawing analogies from a few examples provided in the input. We differentiate between traditional few-shot ICL and other input-based task adaptation methods by emphasizing the importance of demonstration examples. While having more examples generally improves performance, ICL can behave unexpectedly, with results heavily influenced by the specific examples chosen, their order, and formatting. Moreover, language models can also perform tasks based on abstract descriptions without needing explicit examples, which we refer to as instructions. Although both types of prompts fall under ICL, our findings show that they affect internal representations differently, underscoring the importance of input examples. Recently, prompt tuning has emerged as a method for task adaptation, where we learn a small set of continuous vectors that are added to the input while keeping the model's parameters unchanged. This approach strikes a balance between full model fine-tuning and static prompting, allowing for task-specific adjustments with fewer parameters. We also discuss how language models map words to vectors in a continuous embedding space, which is structured through pre-training. The linear representation hypothesis suggests that this space contains feature directions that represent understandable concepts, enabling the model to perform meaningful vector operations. The idea of feature superposition explains how a model can handle more features than there are distinct directions in the embedding space by using nearly orthogonal vectors for feature encoding. To uncover these encoded features, we can train linear probes to extract information from the embedding space. Previous studies have shown that these features can represent part of speech tags, parse tree structures, and higher-level semantic attributes. However, there is still a lack of understanding regarding how the context before a given input, especially during task adaptation, influences feature representation. We also highlight that the structure of representations in the embedding space is crucial for task performance. For classification tasks, this means that representations of inputs belonging to the same category should be well separated from those of other categories. The concept of manifold entangling has been a key idea in neuroscience. The manifold capacity framework provides a formal connection between the geometry of representations and their separability, measuring how effectively task-relevant features are encoded. By examining how different prompting methods impact manifold capacity, we can gain valuable insights into the internal dynamics of ICL and the effectiveness of various task adaptation strategies. Section Summary. In this section, we explore the computational flexibility of modern language models, particularly focusing on in-context learning, ICL, and how different prompting methods influence internal representations and task adaptation. We aim to uncover the geometric properties of category manifolds in the embedding space, revealing distinct mechanisms behind ICL despite similar performance outcomes across various prompting strategies. Section: Dataset Details. In this section, we describe our dataset and task setup. To explore how different prompting methods affect representations in specific tasks, we needed a dataset that allowed us to control multiple text categories. We found that existing text classification datasets lacked enough samples and a comprehensive multi-label scheme for our analysis. As a solution, we used a separate language model, Claude 3.5 Sonnet, to create a synthetic dataset that met our research needs. This dataset includes various sentences, each labeled with 3 types of categories: sentiment, topic, and intent, with 5 categories for each. This multidimensional labeling enabled us to study representational effects in a multitasking context. We consistently used this dataset across all experiments, focusing primarily on sentiment classification. To confirm our results, we also repeated key single-task experiments using established open datasets as a control. Detailed information about the datasets, including how they were generated, category distributions, and example sentences, can be found in the appendix. Our research centers on text classification tasks with a fixed set of categories, as these tasks have a clear connection between the geometry of representations and the separability of categories in the embedding space, which ultimately affects performance. Unlike traditional encoder-based models that train separate classifiers for each category, we focus on decoder-only language models. These models can be prompted to generate class labels directly from the vocabulary. This approach introduces 2 important factors that influence performance: representation quality, which refers to how well the underlying representation can separate class manifolds, and readout alignment, which is about how well the model's unembed layer aligns with the ideal decoder directions. Manifold capacity theory helps us separate these components by measuring representation quality at each layer, regardless of the specific unembed module used for vocabulary output. We compared 2 main types of natural language prompting in our work. The instruction prompt includes a specific format, using sentiment as an example, where we present a test sentence and ask for its category. The demonstration prompt consists of several examples in a similar format. As a baseline for our representation analysis, we also extracted embeddings using the raw sentence input. Analyzing the representational geometry in decoder-only models comes with unique challenges, such as masked self-attention and dependencies on the last token. To tackle these challenges and examine how prompting affects representations, we considered 2 types of embeddings: sentence embeddings, which are derived from the tokens of the input sentence alone, and last token embeddings, which focus on the last token's activations at each layer. These embedding types and the potential effects of prompting are illustrated in our figures. To analyze the representational geometry, we first created category manifolds by gathering the embedding vectors of all sentences that share a class label. For a classification task with multiple categories, we can think of the resulting representation as distinct collections of vectors in the embedding space. We then computed several properties of this collective representation. Manifold capacity is a positive measure that indicates how separable the category manifolds are, with higher values signifying better separability. It can be understood as the number of classes that can be linearly distinguished per dimension, reflecting how efficiently the manifolds are arranged in the embedding space. We provide a more detailed explanation of capacity in the appendix. For the geometry of individual manifolds, we simplified our approach compared to previous formulations. We measured the dimension of each manifold using the participation ratio of principal components, which corresponds to the number of dimensions needed to explain a significant portion of the variance. The radius of each manifold was defined as the maximum distance between any 2 points on it. We averaged these metrics across manifolds to obtain single scalar values, which we refer to as the geometric properties of individual manifolds, as they do not depend on the relative positions of the manifolds in the embedding space. Section Summary. In this section, we describe our creation of a synthetic dataset using a language model to explore the effects of various prompting methods on text classification tasks, focusing on sentiment, topic, and intent categories. We analyze the representational geometry of decoder-only models by examining sentence and last token embeddings, measuring manifold capacity and geometric properties to understand the separability of class representations in the embedding space. Section: Correlation Structure. In this section, we explore the correlation structure, which refers to how the arrangement of individual manifolds affects their capacity. We assess correlation coefficients between the axes of variation of these manifolds and their centroids. We consider these measures collectively to understand how the spatial relationships among manifolds influence capacity changes, rather than focusing solely on individual manifold properties. Our results show that prompting significantly impacts the internal representations of language models, revealing distinct patterns at various processing stages and with different prompting methods. When examining representational changes during a text classification task, we first compared the effects of demonstration prompts and instruction prompts in a typical in-context learning (ICL) setting. We found that instruction alone led to good accuracy, outperforming demonstration prompts with fewer than 5 examples. However, with more than 5 examples, performance improved beyond that of explicit instruction, quickly reaching a plateau. Replacing meaningful category words with abstract letters required more demonstration examples for the model to understand the categories. When category labels were shuffled, the model struggled to generalize, indicating it relies on existing associations rather than learning entirely new tasks. At the sentence level, we observed that demonstration examples reorganized intermediate representations significantly, enhancing the separability of sentiment manifolds by reducing their dimensions and improving correlation structure. Interestingly, the geometry resulting from demonstrations was similar across different labeling strategies, suggesting that the input distribution examples primarily influence sentence representation. Regarding last token effects, we found that instruction prompts increased manifold capacity compared to raw sentences, with noticeable effects starting from layer 8. Demonstrations further enhanced manifold capacity, even when task performance was lower with fewer examples. This indicates that while instruction achieves better accuracy due to alignment with category manifolds, demonstrations improve both alignment and representation structure. Even a couple of demonstrations lead to a more optimal representation than instruction alone, although this improved separability isn't fully utilized by the unembed layer. We also noted that last token capacity was lower for letter code labeling compared to category words, which explains the reduced performance when output labels lack meaningful semantics. We investigated the sensitivity of few-shot ICL performance to the choice of demonstrations, noting that performance can vary significantly based on the examples and their order. We analyzed the relationship between last token manifold capacity and performance across various random samplings of demonstrations. We observed considerable performance variability, especially with fewer examples, but the changes in manifold capacity at the final layer were minimal, even in low-accuracy scenarios. Finally, we examined whether prompting for one task affects representation quality for unrelated tasks. We created a dataset with 3 independent sets of labels, allowing us to classify sentences by sentiment, topic, or intent. We generated instruction and demonstration prompts for each task and computed representational metrics for the different sets of manifolds. We categorized cases where the manifold labels matched the classification objective as coherent and those where they did not as incoherent. This setup enabled us to investigate how prompting for one task influences the model's internal representations for other tasks using the same input. All experiments utilized gold category labels, and we normalized manifold metrics against the raw sentence case. Section Summary. In this section, we analyze how the correlation structure of manifolds influences their capacity and how different prompting methods affect the internal representations of language models during tasks. Our findings indicate that while instruction prompts yield better accuracy, demonstration prompts enhance representation structure and manifold capacity, revealing complex dynamics in model performance and sensitivity to example selection. Section: Synergistic effects at the sentence level. In this section, we explore the synergistic effects at the sentence level. We found that increasing the number of demonstrations significantly boosted the capacity of intermediate layers for coherent tasks, while the impact of instructions was much weaker. Interestingly, even for incoherent tasks, more demonstrations still increased capacity, though to a lesser degree. This suggests that providing example sentences can enhance representation capacity for related tasks, even if the tasks differ. While both coherent and incoherent scenarios showed a similar trend of increased capacity with more examples, the increase was more pronounced for coherent tasks. The difference between coherent and incoherent settings likely stems from changes in how the manifolds are correlated and positioned in the embedding space, rather than just the geometry of the manifolds themselves. Next, we examined task interference in last token representations. Our analysis revealed a unique pattern. In earlier layers, more demonstrations for incoherent tasks increased capacity, but this trend reversed in later layers, where additional examples decreased capacity. Coherent demonstrations consistently increased capacity from layer 12 to the final layer, indicating that task-specific input-output pairings play a significant role. The decrease in capacity at the final layers suggests a representational trade-off, where features for irrelevant tasks are compromised to enhance the separation of relevant features. This effect was not explained by the geometry of individual manifolds, as we observed a reduction in dimension for both coherent and incoherent tasks. We then shifted our focus to soft prompts, an alternative method for task adaptation that optimizes a task-specific prompt in the embedding space. This approach allowed us to investigate whether gradient-based methods affect internal representations similarly to traditional prompting. We trained separate soft prompts of varying lengths for 3 tasks and found that soft prompts consistently outperformed demonstrations, with no significant correlation between final performance and prompt length. Given the similarities in performance across different prompt lengths, we focused on a representative 5-token soft prompt for our analysis. Our analysis of sentence-level representations during soft prompt training revealed a significant difference compared to hard natural language prompts. The optimization-based solution did not alter intermediate representations in earlier layers, unlike other prompting methods. Instead, the effects were concentrated in later layers, where incoherent prompts led to decreased capacity. This capacity difference could not be explained by the geometry of individual manifolds, highlighting the importance of relative manifold arrangement. At the last token level, prompt tuning also showed distinct effects. For coherent prompts, capacity increased significantly in later layers, surpassing instruction-prompted capacity but remaining below that of demonstrations. In contrast, soft prompts for incoherent tasks dramatically reduced the capacity for unrelated tasks, indicating that gradient-based optimization compromises the representation of irrelevant features more than natural language demonstrations. The capacity difference between coherent and incoherent settings was primarily due to the alignment of manifolds in the embedding space. In our discussion, we highlighted how language models adapt to various tasks by analyzing the geometry of internal representations under different prompting methods. We found that zero-shot instructions, few-shot demonstrations, and soft prompts achieve comparable performance but operate through different mechanisms. Zero-shot instructions mainly influence the final processing stages, while demonstrations reshape intermediate representations to optimize for classification. In multitask settings, demonstrations enhance early layer representations for multiple tasks, suggesting a general feature enhancement from diverse input examples. Soft prompts, while trained on the same examples, mainly affect later layers responsible for output preparation. A key insight from our analysis is the distinction between representational geometry and readout alignment in determining model performance. Manifold capacity measures the separability of category representations, but actual performance also depends on how well the model's unembed layer utilizes these representations. We identified two notable failure modes in few-shot ICL: sensitivity to example choice and ordering, and limited generalization beyond pre-training label associations. Despite well-organized internal representations, the unembed layer may not effectively leverage this structure, leading to poor accuracy. High separability suggests that training a simple linear readout on top of existing representations could improve performance. The success of prompt tuning supports this view, as its effectiveness seems to stem from better alignment between representations and the vocabulary readout layer, rather than altering the geometric organization of the embedding space. Our findings suggest two promising research directions. First, optimizing readout alignment could enhance performance, and second, direct geometric optimization of representations could lead to innovations in language model prompting. We anticipate that insights into LM representational geometry could improve performance and stability across various objectives. Section Summary. In this section, we explore how different prompting methods, including demonstrations and soft prompts, affect the internal representations of language models, revealing that while demonstrations enhance manifold capacity significantly, soft prompts primarily influence later layers without altering earlier representations. Our findings suggest that the effectiveness of these methods stems from their distinct impacts on representation geometry and readout alignment, highlighting opportunities for optimizing model performance through better alignment and geometric strategies. Section: Limitations. In this section, we acknowledge the limitations of our study, which offers insights into the representational geometry of language models with different prompting methods. First, we utilized synthetic datasets created by Claude 3.5 Sonnet, allowing us to control task parameters precisely. However, this may not fully reflect the complexity and variability found in real-world language. To improve the generalizability of our results, we should consider testing with a wider variety of natural datasets in future research. Second, the metrics we use to measure representational geometry, like manifold capacity and individual manifold geometry, while useful, oversimplify the intricate tasks that language models perform by concentrating on a classification task with specific target labels. Future studies should explore how other tasks, such as those needing multi-token outputs, like chain-of-thought prompting, influence representational geometry. Additionally, employing more sophisticated measures that connect geometry to complex computations could offer deeper insights into the subtle changes that occur during task adaptation.